Hi, this is Dev again. In this video, I will be demonstrating my solution for the reinforcement assignment. But for the demo, I'll focus on the W track so we can actually see the behavior clearly. First, I'll show you one sweep of value iteration on the W track with the nearest crush mode. Here, as you can see in the first table, these are the sample of state near the starting area. The value is stored as row column, then WX and WY. So this is for the V. This table is for V before, and at the beginning everything is zero, so this table is all zeros, as we can see over here. And then I'm also running one Bellman sweep over here, um, over the state space. Down here I print single value iteration sweep completed, as we can see over here. For V after everything is 1.0. Now, along with the V after value 1.0, and for all of this data, I'm also showing the greedy action that currently minimizes the expected cost from the state. in in this slice of the state space, the greedy acceleration is consistently -1 and -1 for both x and y, which is one of the 9 possible acceleration pairs. So this demonstration how in one sweep value iteration takes the model of the racetrack, evaluates all the actions from each state using the simulator as a generative model, and lastly it updates all the v values. Next up, I'll demonstrate q learning q value updates along one sequence or a single trajectory. In this table, all the data is generated again on the W track with the nearest crashes. Each action field tells us that the acceleration was ignored due to 20% failure probability. So let's take an example, this initial state that is 7100. Um, over here, the action is -10. The next state would be 7100 again. Um, in here, the crash is true. So the value old Q will be. So that was it for Q learning. Now, likewise, this demonstration is for SARSA algorithm with all the identical columns. Here, the difference is in how the update is computed internally. SARSA uses the on policy update. So if I look partway down the table, I can see some of the state action pair getting more than once. For example, a state might start with 0, uh, then it will get bumped to 0.5, and then later get bumped to 0 again when we revisit it with a different future return. That SARSA slowly shaping Q based on the policy it's actually following. Now, next up is exploratory versus greedy actions. I'm splitting the Q learning logs into exploratory and greedy decisions. So in the first table, this is for exploratory actions, where all the values for is exploratory is true, and in the second table, that is greedy actions, all the is exploratory values are false. So in this first table, it is true, so epsilon greedy ignored the current best action and picked a random acceleration. We can see that some of this still lead to action failed equals to true. That's true of this, um, which is the environmental randomness on top of exploration. So this clearly separates the exploration mechanism, the random action choice controlled by epsilon, from the non-deterministic part of the simulator, which is the 20% chance that an acceleration just doesn't take effect. Now I'll show complete greedy trajectories after training. In the previous cells, I trained 3 agents on the W track with nearest crashes, one value iteration agent that runs to convergence, and Q-learning and SARSA agents, each trained for 500 episodes with a smaller epsilon, so they are most greedy. Now, using these helper functions, I rolled out a greedy path for each policy and logged the sequence of state action and next states triplets. Now, so the first table is value iteration greedy path. It is very short, it just have 10 steps. Because the value iteration policy is close to optimal, the car accelerates cleanly from the start to the finish with lines with no crashes. So these are all false, and once it's done, it turns into true. So similarly for Q learning greedy path, over here, it is much larger. There's like 200 steps for Q learning. Um, We can see that the lines where crashed is true, and some lines where action failed flips between false and true, even though the action is same. There's the non-deterministic response of the simulator along the path. So that's it for Q learning. Now next up is SARSA. SARSA takes around 25 steps to finish. So this one also have a similar feel. The car moves down the track, sometimes crashes and restarts, and we again see action fail toggling. These three tables satisfy the requirement for to show to show the actual value with the triplets state, action, state for each algorithm, and it also highlights where randomness in the environment changes the outcome, even when a fixed greedy policy. Next, I will be demonstrating the crash and clipping behavior more explicitly in the nearest crash mode. In this cell, I am driving this car into the wall using a simple sequence of actions. We can see that the restart position is the nearest track cell to the crash point. So to detect the collision, I am using the present Helms line algorithm over here, df line nearest function. So this table lists the discrete row and column cells, that is 6, 1 and 7, 1, that lie on the line segment. If any of those cells is a wall, I flag a crash. So this is my clipping algorithm for detecting whether the car's continuous movement intersects with the track boundary. And finally, here is the same type of crash demo, but now the environment is in the restart crash mode. Again, I log each time step in df crash restart, which is this one. And when crashed becomes true, we can see that the restart state is no longer the nearest track cell. Instead, the position jumps back to 0, 0. The episode does not end. The time trial keeps going. So long trajectories can include several full restarts from the starting line. Thank you and signing off.